So there is also a feedback view of understanding the oscillation in the cross-coupled LC oscillator we have just discussed. So if I redraw the earlier circuit where we had combined two differential oscillators, then we had these two inductors, two capacitors, and two resistors modeling the loss of the tank. Along with this cross-coupled pair. And here we can see that all these nodes are anyway going to be virtual ground. So we can as well just short them. R, M1, M2. So now this circuit, if we look in another way, it appears as if we have got one half looking like a tuned common source amplifier where M1 is the amplifying element, and at the drain we have got this tuned load connected, and this amplifier is getting the input from the drain of M2. So if I have to redraw the circuit in this manner, then it appears as if I have got this one L, C, R tuned load, which is connected to the drain of M1. Similarly, there is another tuned common source amplifier formed by this M2. Name this as VOP, VOM. Then in such a scenario, this is the VOP. And here is the VOM. And we can see that its gate of the M1 is coming from VOM, and the gate of M2 is coming from VOP. So we can make this connection. So this output is going to the input of M2, and output of the second stage is connected to the input of first stage. So here it looks like as if we have got two tuned common source amplifier which are connected in a loop. These are two source tuned amplifiers connected in a loop. Okay. Here LCR, LCR. So now we can see that this looks like a feedback system where we can think of these two stages as the forward path in a feedback system, and the output is going back to the input. So now let's say that these MOSFETs are biased in saturation with transconductance of GM. Then we know that at the resonance frequency, the load for each of these amplifiers is going to be just this R. Then the gain of each stage is going to be minus GM into R. And if we go around the loop, then overall gain is going to become GM into R whole square. So the loop gain at omega naught is equal to 1 by root over LC. G at J omega naught is going to be equal to GM into R whole square. And we know from the Barkhausen criteria for oscillation, this loop gain magnitude should be equal to 1 at the frequency of oscillation, as well as the loop gain phase should be equal to 180 degree, assuming negative feedback. So this Barkhausen's criteria mean that if you have a feedback system, let's say which has a loop gain of Lg, and the feedback is with negative polarity, then for sustained oscillations at the output, we want this loop gain to have a phase shift of 180 degree. So it means there should be a polarity inversion already in the loop. In addition to that, Lg should also give a polarity inversion. This loop gain should have a gain of 1. So it means even when there is no input supplied, this output is going to appear at the input of this forward path. And since there is a complete 360 degree phase shift in the loop, we will find that the output coming out of this forward path is going to be same as the output which we started with. So as a result of which, even in the absence of input, we can have an output which can be maintained indefinitely. So if it is possible to achieve such a loop gain at a frequency omega naught, then that oscillation is going to be self-sustained even when there is no input applied. In our case, if we go around the loop, then we can see that there is also going to be a 360 degree phase shift at omega naught, because at omega naught we are going to get a overall gain of only GMR square. These reactive components are going to just tune each other out. So it means that for the cross-coupled LC oscillator, if we want sustained oscillation, this Lg at G omega naught and should be equal to 1, because it should have a 360 degree phase shift as well as gain of 1, implies GMR to be equal to 1. This is in cross-coupled oscillator. So this is the same relation which we have got earlier also when we were discussing about power supplied by the active circuit is equal to the power lost in this resistance. That condition was when GMR is equal to 1. Here also we can see that we are getting the same condition when we are looking at this cross-coupled LC oscillator from the perspective of a feedback system.